Well, it's 4 p.m. Welcome everyone to the Physics Department Colloquium. Today it's my great pleasure to welcome Dr. Martin Formanek to give us a colloquium about flying focus at Eli beamline. So in case you don't know, Eli is an infrastructure project in Europe where they built to be the most powerful laser in the world. It's close to the top, if not already at the top at the moment. Dr. Formanek earned his bachelor's and master's degrees from Charles University in Prague. Then he moved to the US on a Fulbright fellowship, which enabled him to pursue a PhD in physics at the University of Arizona, Tucson. After completing his degree, Martin worked as a postdoc at Max Planck Institute for Nuclear Physics in Heidelberg, Germany, with Antonino Di Piazza. Since 2022, he is employed at Eli Beamline Extreme Light Infrastructure facility near Prague in the Czech Republic. At Eli Beamline, he studies strong field electrodynamics in flying focus pulses as a Mary Skłodowska Curie Fellow. So without further ado, let's welcome Dr. Formanek.
Okay, thank you so much for the nice introduction and also for the invitation to come here and present at this beautiful place. This is a picture which I took yesterday from Mount Sanitas, and I really enjoyed the nature around Boulder. So, as Yuan said, I'm going to talk about, does this work? It stopped responding. Yeah, I think we left it sit for too long. I think we left it sit for too long. Okay. Okay. Nope. That didn't work. Oh, did it? Okay. Oh, okay, that worked. Great. So I will be talking about the flying focus pulses. I will let you know a bit about my institute, Eli Beamlines. I will tell you about strong field QED and what it is, why we study it, and then what are flying focus pulses, how do we prepare them and describe them, and then some projects which we did with flying focus pulses in the strong field regime. I would like to thank my collaborators. I started this project at Max Planck Institute in Germany with Antonino Di Piazza. He's now a professor at the University of Rochester, and I also did this project with John Palastro and Dylan Ramsey, who are at the LLE. Some parts we also did with Maria Vranic from IST in Lisbon, and this is my boss at Eli Beamlines, Dr. Stefan Weber. Here are the institute logos. So just to introduce you Eli Beamlines, this is the facility. It's in a small village just outside of Prague in Czech Republic. So we typically live in Prague and commute to get there. This is the overlay of the facility. We have 4 laser systems, which are on the ground floor of the building. And then we have experimental halls underground. We have E1 to E6 experimental hall. We are called beamlines because we are producing beams of secondary radiations. We produce electron beams, proton beams. We have X-ray beams from a betatron. We have gamma rays, which are further used. We are a user facility, so we have 2 user calls per year where people can apply for a time on not only the lasers, but any of the beamlines, and then use and come our facility for free of charge. Just have to pay for the travel and for staying at Prague. And this is the overview of the lasers. L1 and L3 lasers are already operational and are open for users. the lasers differ in what is the energy in a pulse and what is the peak power, pulse duration, repetition rate. You see that as you increase the energy in the pulse, the repetition rate goes down, as you would expect. And the L4 laser, which will be our most powerful laser, up to 10 petawatt, is currently in operation, but in nanosecond regime. It's still not compressed to 150 femtoseconds when it will reach the 10 petawatt. But it's already useful for some fusion studies, and people are applying for time on that. And L2 laser, which also is supposed to be commissioned this year, is not operational yet. So that's the overview. And now I like this plot a lot. It basically shows how the lasers developed over time since their inceptions. So the theoretical principle comes from Einstein in 1917. And it took a lot of decades until we built a first laser on the principle of stimulated emission of radiation. That was by Theodore Maiman in the US in 1960. And since 1960s, the peak power of laser systems increased quite exponentially. You see that this is a logarithm scale. And now in like 2022 at 10 petawatt, we are about 16 orders of magnitude more than in 1960s. So that's quite a progress. What allowed it is the invention of chirped pulse amplification, which was developed in the 80s in Rochester, actually. And now it's used for a lot of the systems, and there was a Nobel Prize for it in 2018. And recently, in 2023, there was also a Nobel Prize for laser development, and that was for development of attosecond pulses, which went to Ferenc Krauss and Lurie. And our sister facility of ELI, there are three facilities. One is in Hungary. That's ELI attosecond that deals with attosecond pulses. Between these two Nobel Prizes? This Nobel Prize was basically for increasing the peak intensity of the lasers, of like allowing more power to be squeezed without destroying the optics. That's the chirped pulse amplification. The attosecond ones is the way how to shorten the pulses, how to make as short pulses as possible. Yeah, it's a good question. All right. So why we study strong field QED? Also, I should say, like at this graph, if you look at it, it's not only like the peak power, but also what abilities it opens you to study. Because laser is a tool about which we know everything. We know like what is the phase, what is the power, what is the frequency. It's a good tool to study physics. And as you go up in the peak power and intensity, you open up new windows of physics which you can explore. Like you start with like ionization of molecules, ionization of atoms, then you get into the regime where you get to relativistic effects, you can accelerate electrons, and finally at the 10 petawatt-ish scales, you open the quantum physics where you can study effects of quantum electrodynamics. So the quantum electrodynamics studies processes in plasma in extreme astrophysical environments, like for example in pulsars and magnetars, in accretion disks of black holes, quasars, cosmic radiation, also in the primordial plasma in the universe during BBN. You can see some QED processes in heavy ion collisions, and laser is a great tool to probe such environments because you don't have to go to space to see such extreme environments. You can recreate them in laboratory. It's called astrophysics in laboratory, and that's now studied. And there are a couple of interesting review articles I would refer you to. There is the classical one from 2012 from Di Piazza, but even a recent one from 2022, 2023, which have like comprehensive overview of the field. Okay. So I will now do like a bit introduction, like what we study, how we study it, what tools we are using it. So electromagnetic field scale, you need to have a sense of like in which regime of parameters you are operating. And there is something called Schwinger critical field. And the Schwinger critical field is defined as a field which does work equal to the electron rest energy over distance of reduced constant length. If you calculate what it is, it's like 10 to 18 volts per meter, which seems quite high. But for example, in heavy ion collisions on colliders, if you have a lead-lead collision at 3 TeV, you get much higher field than that, 10 to 24 volts per meter. But such field is very, very short-lived. It lasts only as long as the ions are passing each other. So it doesn't live long. In laser field, we have much longer-lived fields. This also corresponds to critical intensity, which is 10 to 29 volts per centimeter squared. And laser work record, which was published in 2021 in Korea, is like 10 to 23 volts per centimeter squared. So you see that we are still like 6 orders of magnitude below the Schwinger critical field intensity. And you saw the previous plot when I was showing you the exponential progress of laser technology. So maybe in a couple of decades, we will get even there. There is also equivalent magnetic critical field, which would be 10 to 9 Tesla. And again, in nature, you can find fields which exceed that, like, for example, around magnetars. Yes?
So that critical field is that?
Yes, exactly. You get to the electron-positron pair production in vacuum. We are still not quite yet with lasers, but we can still study some processes already. How do we characterize electromagnetic field? So maybe you are familiar from your EM classes that there are field invariants for electromagnetic fields. This is the F and G, E squared minus B squared, E dot B. And such invariants are not very useful for studying lasers, because if you approximate laser just as a plane wave field, which pretty much all lasers are similar to that around focus, these two are zero, because you have the same amplitude of E and B, and they are orthogonal. So these two invariants won't tell you much about the laser. So that's why we actually describe something called collision invariants, and that's how the laser pulse collides with a particle, whether it is electron or a photon. And for electron, you can define that it's this invariant quantity. And basically what it is just the electric field which the particle sees in its rest frame. So the ultra-relativistic particle can see some magnified, Lorentz magnified field, and you compare it to the Schwinger critical field, and you get some expression. For photons, it's difficult conceptually because you don't have any rest frame of a photon, but you can use the wave vector of the photon to construct similar quantity, and you got the quantum invariant for a photon as well in the collision of a photon with a laser pulse. And then we also have a normalized amplitude of the field, basically the strength of the field. And for plane wave field, it's basically the square of its fourth wave vector, normalized by E over MC. And just so that you have an idea, the Schwinger field corresponds to A0 of like 400,000. Typically, the state of the art right now is that we can get to like 100. The chi invariant depends on how fast the electron is, how ultra-relativistic it is. You can look at this plot, and basically here, if I increase the field strength, I get to relativistic effects and multiphoton effects. If I am increasing chi, so even like the electron energy, I get to quantum effects, which is photon recoil pair production. The threshold for relativistic effects is around A0 equal to 1, which is like 10 to 18 watts per centimeter squared. And if you remember that I told you that the record now is 10 to 23, so we are like very firmly in the relativistic regime. And for the quantum invariant, the quantum effects, chi E corresponding to 1 corresponds to like a field of like 10 to 23 volts per centimeter squared for the electron, and the critical one is 10 to 29. So we are just getting like to the quantum regime where we can probe it. We are not in the non-perturbative regime yet at 10 to 29 million orders, 6 orders of magnitude below that, but we are starting to see the quantum effects with current state-of-the-art lasers. So what such effects are? We'll talk a bit about that. First, like how we studied such processes. So we have some theoretical tools. we have a locally constant cross-field approximation. So what is that? It allows calculating processes or probabilities of processes for arbitrary fields from known results in a constant crossed field. And why is that? Because if you have a fast enough particle, ultra-relativistic particle, the such particle in its raster frame will basically just see a constant crossed field with equal magnitude of electric and magnetic field and orthogonal component. And that's because of the Lorentz transformation. You know that the parallel components of the fields don't transform, and the perpendicular components get amplified by a gamma factor. So the faster particle is moving, the more enhanced the perpendicular components are. And because the invariant stay invariant, you know that E dot B is the same no matter who is observing it, if it is in laboratory or rest frame, and the same for E squared minus B squared. If you compare them with the energy density in such field, it scales like 1 over gamma squared for both of these invariants. So that means that the faster the particle is moving, the more enhanced the perpendicular component are becoming. And this invariant tends to 0, so they are orthogonal. And this invariant tends to 0 compared to the energy density. So they have the equal magnitude component. So basically, no matter what field you start with, if you are moving fast enough, you will just see crossed fields of the equal magnitude. So that's behind our approximation, which we are using to study fields. And locally constant means that basically from the small segment of the trajectory where a photon is emitted for an electron, the field doesn't change much. So you can say that it's just locally constant field. And that's a basis of a lot of like numerical simulations, for example, MPIK codes. And yeah.
So you call it QED, so field reaction. It's from the point of view of creating this positron there.
Yeah, it's a QED regime.
From the point of view of you need probably your large number and number of photons is large in the field.
Like typically what we do is that we treat, let's say this page, that we treat the external field as a classical.
So
Yeah, and yeah, like the external field is classical, and we treat the emitted photons as quantum, and the from the electrons, which are also quantum. So that's this page actually. That's another theoretical tool which we use. It's a Fourier picture. Basically, you are probably familiar with Dirac equation, which you can solve, and you get the plane wave solution for electrons. And now, if I input here the external classical field of the laser, you can still solve this equation for plane wave field and get a solution which is called Volkov solution. It looks like something like this. It's not quite important, but you can take this solution instead of the plane wave field and construct your quantum field theory on the basis of this asymptotic state, that you have electrons in the laser field dressed. And we draw such diagrams like Compton scattering or Bright-Wheeler process, where you have dressed electrons or positrons in this background field with these asymptotic states, and they can emit a photon by interacting with the external field, or gamma photon can decompose into electron-positron pair. Such process is not kinematically allowed normally in the free theory, but here it's possible because you have this background and the interaction with the laser field. That's the dressed particle state. It basically sums up interaction with like n photons, like as many photons as you want. Okay. And okay, so let's talk about some processes. So first I will start with radiation and the classical radiation. You are probably familiar with the book of Jackson. If you look into this book, you will find in one of the chapters, he says that there are actually two separate theories of electromagnetism he teaches in this book. One of the theories is that I give you prescribed fields and a test particle, and I ask you how this test particle will move in this field. And you can calculate that. You have the Lorentz force, you know how it will work out. The second theory is that I give you sources, the charges and currents, and I ask you to calculate the fields which they produce. And you can also do that. There is like a Linear-Wichert solution of Maxwell equation where you know the trajectory of your particle, you know what fields it emits. But these two theories don't talk to each other much. Like you don't know like what is the back reaction on an electron because it radiates. It's the famous problem of the radiation reaction. You know that the emitting radiation, particle emitting radiation must change its trajectory because it loses energy and momentum. And there was a first attempt to solve this was in 1937. There was a Lorentz-Abraham-Dirac equation, which looks something like this. It amends the Lorentz force by the radiation reaction term. And such equation has issues because it's a second-order derivative of the force velocity. That brings with itself that you have to have another initial condition. This equation has runaway solutions, so it's not very tractable. If I just gave you a stationary electron, it would run out to infinity, but while increasing velocity. There were ways how to fix this. There is a Landau-Lifshitz equation, which basically solves this equation perturbatively, takes the external force as the first order of approximation for acceleration, and then puts it in and iterates. And you get basically a series, and you can like get the first order approximation of what is going to happen. Some people even write that Landau-Lifshitz equation should be the fundamental equation for classical radiation reaction. There are a lot of paper about it. It's still a huge discussion among people, like what is the classical radiation reaction and should we even study it? Because when you get to quantum regime, it will be superseded by quantum physics. So the question would be, is there any regime where this equation is not valid and quantum physics is still not valid yet? And that's something I cannot tell you if that is or not. Tau zero is like a characteristic emission time. It depends on the charge and the mass of the electron. It basically gives you a scale on which this emission happens. Yeah, classical. Yeah, if you take a classical electron radius and speed of light, it's basically the time it takes for speed of light to cross the classical electron radius. It's a very short time, but like the emission is still governed by the Larmor formula, and you get like normal spectrum, like from the Linear-Wichert potential, like this. It's just a parameter, the tau zero. The optical cycle, typically we take like 10 to minus 15, like femtoseconds. Yeah, it's shorter. So the quantum radiation, like which supersedes the classical one in the parameter space where quantum physics applies. The energy of the emitted photons is now comparable to the energy of the electrons itself. So when they emit, they lose a big part of their energy. That means that there is a recoil, the electron feels that it lost the energy. There are discrete instantaneous recoils along the trajectory of the particle, which are determined probabilistically. Like they can happen at any point in the quantum picture. That's opposite to the continuous force in the classical case. And because it's a stochastic process, it can happen that in some configuration, there is the electron can pass through the field without emitting any energy, which wouldn't happen in the classical case. The classical limit is that you just have like a lot of photon emission from small segments of the trajectory. I will be talking about the measurements a bit later. And Bright-Wheeler pair production, that's the other diagram, that you can have a photon which decomposes into electron-positron pair. So far, the linear one, when you would have just interaction between one and one photon, was not observed. But in laser field, in multiphoton, when you interact with n laser photons, that's observed now routinely. You get electron-positron pairs. It's also important for astrophysical processes. You can imagine now that since we have these two processes, you can combine them. You can like chain them behind each other. And you start with like single multiphoton Compton or Bright-Wheeler process. And then if you string them together, you get into QED showers or avalanches, depending if you are driving it by laser energy or by particle energy. And if you look at this parameter space, we are about chi is equal to 1, the quantum parameter, at around 10 petawatt. So we are still into like a single process regime. And we are only starting to get into like the shower and avalanche regime. So that's like also prospect for the future to be able to observe such processes. And finally, one process I wanted to talk about is vacuum polarization. Vacuum polarization is that if you apply strong field to an empty space, to vacuum, it becomes polarized. And that's a measurable thing. If you write a Lagrangian of the electromagnetic field, in the lowest order in field, you can get an interaction correction because of the quantum effect. This is the interaction part, which allows you to calculate a polarization and magnetization of the vacuum as a medium. You get such expressions. And now the medium, the vacuum itself, when you apply strong fields, behaves like a medium with material properties. And you can have an X-ray probe pulse going through such a region of space, and you solve Maxwell equations in a medium with some polarization and magnetization, and you get that the X-ray probe pulse will get affected by this. And moreover, such medium has a different properties in E and B direction. You can see this from this polarization. E and B have different terms in magnetization. So that means that the medium is even birefringent. And the birefringent medium, you are probably familiar with calcite crystals. If you look through a calcite crystal on anything, you will get two images because each polarization of light has a different index of refraction in this medium. And the same is true for vacuum under strong fields. And the effect is tiny, very small. There is a huge effort to actually measure it these days. It hasn't been measured in pure optical environment yet. And we did a bit work of like how to do that with flying focus pulses. Okay, so that was a long QED introduction. And now I will talk a bit about what I'm working on. And that is the flying focus pulses. So what are flying focus pulses? Flying focus pulses are laser pulses which allow you to control the position of the focus in time and space. And the first way how to do it is using a chirped pulse, which has colors decomposed, let's say, from blue to red, which passes through a diffractive lens, which has different focal lengths for different colors of the light. So here, if the blue light comes first, it's focused the furthest from the lens, and then slowly, as the other colors come, the red one is focused the closest to the lens. So you get a focus propagating from here to here. That was described in 2018 and also experimentally demonstrated at LLE in Rochester. There was a similar proposal, just theoretical, from France in 2017. I have a simulation which shows how it looks like, which might be better. So here you can see the blue light coming into focus, and the intensity peak is going to the left as other colors come into focus. This is the simulation. No, this is the experimental measurement, which they did. You see a focus forming somewhere here and slowly propagating to the left over quite a macroscopic distance of a couple of millimeters, although it looks very noisy. And the first test from 2018 was very low powered. They used like 10 to 14 watts per centimeter squared. Okay. Since then, there were other proposals how to do flying focus pulses. So another experimental proposal, which is here, it's now doesn't use chirp pulses, but monochromatic pulses. They are reflected from this kind of mirror, which is an echelon stepped mirror, which introduces time delay for each of the concentric circles. And then you focus it with a parabolic focusing mirror, which has a different focal length for different cylindrical cylinders of this light. So you get the time delay from here, and the parabola ensures that you have the space displacement, and you get the flying focus again. Another way how to do this is using a nonlinear media, which has a different index of refraction for different intensity passing through the medium. So you can have a shaped pulse with like some intensity ramp, and each segment of this pulse will get focused at different place, and you get a flying focus. Yes? Exactly. Yes. You are. Yeah. That's a good point. That we are just spreading the pulse, and we are stretching it instead of people who are trying to like focus it as much as possible. And that's kind of a point, because we are trying to observe effects which are normally observed in high intensity pulses, but in much lower demand laser pulses at like terawatts of power for a longer time to achieve the same effect. I will be talking about that. Another way how to do flying focus pulses is to replace the chromatic lens with plasma optics, which has a higher damage threshold, so it would allow for higher intensities of pulses. That was a recent paper from last year. And for the axiparabola echelon, that was already implemented, also at Rochester. This is the picture of the stepped mirror, which they have, like 9 × 9 centimeters. And they also did some tests at low powers to show that they can do the flying focus. And there are also groups which now use just the parabola, which also allows you to have a flying focus pulse, but without the control over how fast the focus is moving. But there are some groups in Israel and in France who will look at that. Okay. So what I am looking at is how particles interact with such pulses. So this simulation, or like this picture, is showing electron interacting with a normal pulse, a normal Gaussian pulse, which is focused at like specific z is equal to 0. So you see that the electron, as it passes the focal region, it interacts with the pulse at the position where it's focused. There are some tails. And pretty much what the electron sees, it sees like the oscillatory pulse modulated by the envelope. On the other hand, in flying focus, I inject the electron to the focus, and since it is flying, it can co-propagate with the electron for a long time. And pretty much the electron just sees plane wave oscillation as it is interacting with this pulse. There is no limit by the Rayleigh range of the pulse as in the Gaussian case. Okay, this is just like how we describe flying focus pulses. Pretty much we take the solution, which is a Laguerre-Gauss solution in paraxial approximation, and instead of the z coordinate of the focus, we take a focus coordinates which is moving in time, eta, which allows the focus to move. And the focal velocity is like -1 minus this epsilon. What is nice is that if you take epsilon is equal to 0, which is the flying focus moving with the speed of light opposite to its phase oscillation, which is exactly the situation which I want for the long interaction with electrons, then this solution is fully analytic. It's not even in paraxial approximation. And if you take epsilon is equal to -1, which means that the focal velocity is 0, you get eta is equal to z, which is exactly the Gaussian solution we know in paraxial approximation. Since then, we developed like other methods how to describe it. You can look at this paper from 2023. It's just like some techniques of finding a solution, displacing the time or space coordinate into complex plane, and then Lorentz transform either with focal velocity or inverse focal velocity for superluminal flying focus, to get the flying focus solution. Nice property of this is that if you take a limit of flying focus going to the -1, which is my situation, you get a match to the previous solution I showed you. Okay, and now a couple of projects which we're looking at. I will start with a not high intensity application, and that is a charged particle beam control with flying focus pulses with orbital angular momentum. You can imagine that the flying focus pulse can have some orbital angular momentum. It doesn't have to be just the Gaussian pulse. And in such case, it creates kind of ponderomotive barrier in the transverse direction, which the electron sees and can be trapped in. This is a longitudinal picture. It looks like this. And now you can imagine that this whole structure is moving together with the electrons as they are oscillating. So they are trapped. And this is just the prescription for the ponderomotive potential, which the electrons see. And you can inject electrons at some radius with some transverse velocity. And of course, like if you are initiating them outside of the ponderomotive barrier, they won't be confined. If they have too high transverse velocity, they will escape. So this picture basically shows you which electrons get trapped. And you can actually get that quite easily just from energy consideration, conservation of energy. And if you account for radiation reaction, if the particles lose energy as they are propagating and radiating, you get even more trapped particles. These are these diamonds here. But this fits quite well without considering radiation reaction. This is just the comparison how such a beam bunch looks like. If you initialize beam bunch, it will spread out quite fast just because of its transverse velocity profile. If you trap it in this flying focus with higher orbital angular momentum, it will oscillate inside of this ponderomotive barrier, and you can even predict the frequency of oscillations from harmonic approximation. So it's just this project. We wanted to use it for like guiding electron beams over some microscopic distance. You know that from laser wave field acceleration, the electrons typically are quite divergent. But if you would trap them in a potential like this, you can propagate them for some distance. The next project is the vacuum birefringence in flying focus pulses. So if you remember, that's the vacuum is becoming polarized by external fields. So typically how it's measured is that you apply strong field to some region of space. Like for example, here we can apply a strong magnetic field and then take a probe photons. Here is a laser, but typically it's like X-rays, which have a linear polarization. So they have a component parallel and perpendicular to the field. And since both of these components will see different index of refraction in this region because of the birefringence property of the medium, each of the component accrues a different phase, and at the end you end up with elliptically polarized light. You have a phase shift between the components, which you can now detect and measure. There was a long-running experiment in Italy, Pavlas, from like 2001, which was doing exactly that. And at the end, there was like no conclusive result. They first predicted they first said they have like much higher effect than they expected from QED. And at the end, I think it was just some experimental issue in measuring. So that was retracted. But now we would like to try to do that with lasers. Instead of like having a constant magnetic field, we will have a region of space with a strong laser intensity and send a probe pulse through that. So that's now proposed. There is a lot of groups around the world who try to do that. So again, in the Gaussian typical pulse, you get the probe laser passing through the focus region quite quickly. In the flying focus pulse, you can have them co-propagate for a long time. And you can calculate what is the phase shift between the components. After some calculation, you will get that it depends on the energy of the laser pulse, on the wavelength of the probe laser, of the probe gamma photons, on the focusing, and then like how well you can overlap the laser pulse and the probe pulse in both longitudinal and transverse direction. And so you see that here there is like no dependence on the time spent in the pulse. which means that both flying focus pulses and Gaussian pulses will give you at the end the same magnitude of the effect as long as they have the same energy. But what it allows you is to lower the requirements on the laser pulse by many orders of magnitude by just co-propagating for a long time. So instead of having very short, very focused Gaussian pulse, you get a spread out long pulse in which you slowly accumulate the phase shift. And the power requirement basically scales as the ratio of the interaction distances in both pulses. So for example, I can take like 15 terawatt pulse with 1 kilojoule and co-propagate X-rays there for a couple of millimeters to accumulate a phase shift which would be measurable today with current polarimetry eventually. So basically, instead of having a very expensive facility such as X-Fells and a very expensive laser of like petawatt scale power, you can have a X-Fel facility and quite low powered, long lasting laser in flying focus regime, which should be much cheaper. And finally, the radiation reaction. So that's the electron interaction with flying focus pulses. There have been quite a lot of effort to measure flying focus, to measure radiation reaction. The first experiment were in 2018 in Astra Gemini laser in UK. Basically, they took a laser, passed it through a gas jet to accelerate electrons, and then collide them with another laser. And such lasers will oscillate, they will emit radiation, gamma ray, which you can measure, and also you can measure the spectrum of the electrons after the collision to see that the electrons lost energy and that you have more gamma rays than you would expect otherwise. And you can compare it and to see that some radiation reaction happened. In the initial experiment in 2018, they suffered from the fact that it was very hard to align the collision so that it would actually happen. And I think that at the end, they got like 4 shots where they conclusively could say that they shot the electron bunch and there was energy lost in the radiation reaction, not quite enough to distinguish between like different modes of radiation reaction. This experiment was now repeated just last year, also at Astra Gemini and also in Korea. There are papers about it out now on Archive and in Nature Photonics. And they have much better statistics now. They, I think, have like hundreds of shots, which they can say that the laser collided with the electrons. So we were also looking at it from the flying focus pulse perspective to co-propagate for a long time. And if you look at the formula, which tells you like how much the electrons lose energy per unit time, depending on the quantum chi parameter, you can be either in the classical regime, where this scales as chi to the square, or in the quantum regime, where this scales as chi to the 2/3. And this difference in scaling is important because in the classical regime, you get that the final energy of the electrons is the initial divided by something which depends on the focusing, on the pulse energy, and on the initial energy of the electrons, but again, not on time. So again, in the classical regime, if you collide Gaussian or flying focus pulse with electrons, you achieve the same effect. Again, you can have much better environment that you don't need high power laser. You can accumulate the energy loss for a long time. But that is not true in the quantum regime. In quantum regime, there is actually a time dependence. And because of this scaling, it turns out that it's more beneficial to keep the electrons in a lower powered pulse for a longer time than it would be in the Gaussian pulse. So this scaling actually helps us, and we will get higher effects. So there is a similar picture as you saw for the birefringence in the classical regime. The power in the pulse scales as like 1 over the interaction time. The intensity is 1 over the interaction time. And you can get the same deceleration of electrons, same energy loss in both flying focus and Gaussian pulses, but in much lower power. In the quantum regime is different. This shows the energy loss as a function of the time in the pulse. And you see that the flying focus pulses monotonically increase the energy loss, whereas the Gaussian pulses have some like peak, and then they go down again as you interact with like much longer pulse than is the Rayleigh range. And that allows you to achieve a higher energy loss with the same by a couple of percent than in the Gaussian pulse. And also, if you look at the photon emission, you get much more photons from this process. You can imagine that if you have electrons in much longer but less powerful pulse, they will emit more photons which are softer. And this is exactly what is happening. Even in the classical regime, that's true. And in quantum regime, it's even amplified because of the scaling. So you get like much higher number of photons emitted if the interaction time is longer than the Rayleigh range of the pulse. And this is the picture how the photon emission spectrum looks like. So in the, like here, I have 10 GeV electrons colliding with 10 joule pulse with some like wavelength 1 micrometer, focusing of 2 micrometers. The electron beam has some divergence, some length. And if you interact with the Gaussian pulse, you see that you have a bit higher emission of the most energetic photons in the GeV regime, and much more amplified emission of the photons in the 1 to here 20 MeV. So you get more softer photons from this inverse Compton scattering process. This is just some details of the simulation that we are still within the Lorentz, the locally constant crossed field approximation. We were just verifying for the emitted photons that they satisfied it so that we can use our codes. So in this concrete example, we got 5 more photons in this range than you would get from the standard Gaussian collision. And in like 1.6 picosecond interaction compared to 227 femtosecond. And the field strength of the Gaussian pulse was like 16. For the flying focus pulse, it was 6. So much less demanding. So that's pretty much what I wanted to tell you. So just to summarize, flying focus pulses are useful in the situation when the long laser particle interaction time is beneficial. For example, you can guide particle beams over some distance, or you can exploit it in the cumulative effects, such as radiation energy loss, when the particles continuously lose energy as they propagate, and also the phase shift accumulation for the vacuum birefringence. And in the quantum regime, the scaling is even more beneficial to extend the pulses on the extent that they are lower intensity, because the scaling gives you benefit for energy loss for the electrons or for the number of photons emitted. And I would like to thank you for listening, and also to European Union for funding this project. Thank you. And if you have any questions, feel free.
I'll give you a mic if you raise your hand.
Thank you for a very interesting talk. Could you go back? I think maybe slide 40. I think.
Okay.
Yes, this specific. Yeah, this specific example. So I'm curious just how. So obviously with the flying focus compared to the Gaussian focus, chi naught drops. So I'm curious, what is the chi drops, or a naught drops. So I'm curious, what is the actual difference in chi between these two scenarios in this example?
You are right. Yeah, I looked at that. I had such a plot prepared. I'm not sure if I could find it quickly, but in the flying focus pulse, you have lower chi.
Yeah.
Than in the Gaussian pulse, but you sustain that chi for longer.
Right. I mean, I guess I understand you. I mean, the numbers are right there in terms of the photons you produce. I was just kind of curious what the actual comparison was for these two cases in this example, or any of the examples, maybe in the last few slides.
Actually, if you look at the, do I have it?
Say, I don't quite have a feeling for how.
Yeah, the chi was pretty much, if you look at these two plots, it was 0.1 times the psi 0 for the 10 GeV case. So
Okay.
Like here you are getting to like chi of like 0.5, and that's where we stop the simulation because you are no longer in the LCFA regime. So you start here at chi as like 3 up to like 0.5. Here you start at chi like 10 up to like 1. This is the difference between these two plots is that you have 1 joule pulse here. Here it is 10 joule pulse.
Okay. I think I can interpret it now. Yeah. Thank you. So okay, and then just to follow up, at the lower chi values, you don't win as much by the flying focus. So I see. So
yeah,
I see.
and because the pulses are shorter, and you don't gain much advantage.
This is what I was wondering: is at what point does chi has to be kind of large enough for this trade-off to be worthwhile? Is kind of the intuition I was probing to see if that was correct. So.
We took a lot of care to still have chi high enough so that we can claim that we are in the quantum regime.
Right. Got it. Thank you.
Welcome.
Hi, that was a really nice talk.
Thank you.
I'm curious, so you talked a lot about how the flying focus, due to the increased interaction length, it decreases your laser intensity requirements. But in order to create the flying focus for a given intensity, you need a higher pulse energy. So do you also decrease the pulse energy requirements, or is it about the same?
The comparisons, all the comparisons we did between the Gaussian pulses and flying focus pulses were at the same energy.
Okay.
Yeah.
Thank you.
So actually, you didn't talk too much about the technology development. So this is a OPCPA laser system based on Ti-Sapphire technology. Was this actually the one which was developed in Livermore? And
so there were experimental demonstrations of flying focus pulses. In the Rochester at LLD, they did it at very low powers with both the chromatic setup and with the axiparabola echelon setup. I think that for the axiparabola echelon, they haven't even used like laser per se, but just like a laser diode to demonstrate that it works. For the chromatic flying focus, they were at the 10 to 14 volts per centimeter squared intensity. So for that, I imagine that they used some CPA.
No, I'm talking about the Eli laser.
At Eli,
yeah.
At Eli, we don't do flying focus experimentally yet.
Okay.
So can you repeat your question?
Well, so what is actually operating then?
Oh,
currently?
At Eli, what we have?
Yeah.
Yeah, we have typically CPA amplification. The lasers are different. Each has like a bit different parameters and different like active medium and.
But it is a OPCPA Ti-Sapphire based amplifier using.
I would have to get back to you for the details.
Okay,
for
you're not on that
lasers,
on that hardware side. Okay. Yeah.
Like the workhorse laser which we have, which is like 1 petawatt, I think that one is a diode pump, and I think it's I'm not sure what is the medium. Yeah.
So I actually have a clarifying question. So you want the counter-propagating geometry to get the Lorentz boost, but you extend the interaction time with the flying focus. So there's no gain you can get to their co-propagating. That they're co-propagated interact for a long time, but it's very low chi.
Yeah, it's a good question. Like why don't we like co-propagate in the opposite direction, and we want the electron to still see all the oscillations of the laser. If you would be co-propagating with the phase velocity, then you wouldn't see the oscillations. You would be co-propagating with those. So we are counter-propagating because we want the electron to pass a lot of peaks and throughs of the laser.
So that's to make them radiate more.
Yeah.
So they
to have like all the interaction.
Yep.
So you had the example of using the orbital, the donut beam to possibly steer and focus a beam. Is this something that's purely conceptual, or do the numbers work out that it could be useful to use something like this in conjunction with a wake field accelerated beam?
So we did this as a study. I don't think that anybody wants to implement it anytime soon, but we compared with other similar proposals of using this. One of them was using Bessel beams and lexicon lenses to also extend the interactions. And our setup was much more energetically favorable because you need a lot of energy to support the Bessel beams for a long time. Here, you are just supporting the small Rayleigh range intensity co-propagating with the electron. Yeah.
Thank you for your nice talk. So the people have tried to measure the vacuum, the birefringence of vacuum in optical cavities too, right? And there are of course systematic errors with the coatings and so on. But how do you get away? Like rest gas in the vacuum is a big problem, and how can you get rid of the problem of the birefringence in your mirrors at this power level?
In the mirrors?
Yeah, so when you measure the polarization of the birefringence of vacuum, right, you are sensitive not only to the birefringence of vacuum. There are many systematic errors that people encounter in the current measurement.
Right.
How can you get rid of that?
So I know that the vacuum birefringence these days is quite a big industry. There are like lots of groups trying to do that. And they have like white papers around about like proposal, how they are approaching it. And I think that they are looking into like all kinds of like errors which can arise from like even like impurity of the vacuum in the cavity and other things which can contribute to the vacuum birefringence. They have it under control to some extent because otherwise they wouldn't be proposing to measure it at expel facilities these days. I know that there are many proposals which also use like some assistance, for example, of high Z atoms, that you would have not only the laser and the probe pulse, but also like some target of high Z atoms, and you would measure the vacuum birefringence in the space around these atoms where you can have combined laser and the Coulomb field to produce like higher vacuum birefringence. So it's a big industry. I can point you to some like white paper of people like proposing how to do that at expel facilities.
Thank you.
So I actually have another question. So for the vacuum birefringence experiments, so people have to, in the end, so they're co-propagating. In the end, you have to be able to calculate how much you expect from such a beam and then to compare that with a measurement. I just wonder, in the Heidelberg-Euler Lagrangian, is it typically working for a constant field, or there's no problem with these more exotic donut-shaped flying focus beam? So is there any issue in calculating that?
It's a perturbative approach. Like you are comparing your field strength to the Schwinger field strength. So in the first order approximation, it works out. You can use that.
Because it's such a weak effect, so it can perturb the effect.
Mm-hmm. Like in the paper which we published about the birefringence, in the appendix, there is a reference somewhere. In the appendices, we have like the whole like calculation done, and it's like, I don't know, like 6 or 7 pages to get to this result in like the first order of perturbative theory and in paraxial approximation and like the first order distortion of the Gaussian probe beam in both like polarization directions, and then subtract.
That's it.
Yeah.
The elaborate calculation.
Yeah.
So do we have more questions?
But it can be done analytical in the first order.
So if there are no more questions, let's thank the speaker again.
Thank you very much.